This is the Building Automation Monthly Podcast with Phil Zito, episode 111. Hey folks, Phil Zito here, and this is episode 111 of the Building Automation Monthly Podcast. And in this episode, we are going to be finalizing the three-part series on control sequences. So if you haven't listened to episodes 109 and 110, I really encourage you to do that. It will help make this episode make a lot more sense. So with that being said, this episode is releasing on the 16th, I believe, maybe the 15th. Let me make sure I got my dates right. Nope, the 16th of April, which is the Niagara Summit 2018. And I will be at the Niagara Summit. So if any of you all want to meet up, just hit me up on LinkedIn or hit me up on Facebook or send me a message through buildingautomationmonthly.com. And I'd love to meet with you and chat and just get to know my listeners even better than I already know most of y'all. Alrighty, let's dive in. So like I said, we're continuing on with our control sequences three-part series. And in the previous episode, we talked through a VAV control sequence, and now we're going from simple to very complex. So we are just hurtling ourselves into the world of central utility plants, specifically chilled water loops. So we're going to unpack a lot of the fundamentals around chilled water loops. And then from there, we're going to dive into chiller staging, and we're going to also talk about some decoupled loop chilled water sequencing. Now, there's not going to be any sequence of operations to follow like there was last episode. I'm not going to have a PDF for you to download. However, there will be a ton of really solid information in this episode. So sit back, relax, and let's dive in. So chilled water, what exactly is the purpose of chilled water? You know, that's a question I get asked quite often is, why can't I just use DX cooling on my rooftop and call it a day? And the reason is that chilled water, when you start to get to high tonnage, okay, so a ton of cooling is 12,000 BTUs, and a British thermal unit is basically a measurement of heat. That's what BTU is. So a ton of cooling has the capacity to remove 12,000 BTUs worth of heat. Now, here's the deal. With DX cooling, that's using the refrigeration cycle, which we'll talk through in just a second, you can only remove so much heat before it becomes prohibitive for you to go and run a essentially DX system, because you're going and using it right there on that airstream. And there's only so much heat you can transfer out of an airstream. However, with chilled water, what you're able to do is you're able to use that same DX process, but you're able to remove larger quantities of heat from water. And if you didn't know this, water is able to hold a lot more BTUs than air. So air can only hold a certain amount of BTUs, and water can hold a lot more, and steam can hold even more. That's why steam is often used for heating, and hot water is used for heating as well. But we're focused on cooling here. Now here's the deal though. So this water is able to go and have a lot of BTUs in it. Where does it get these BTUs? Well, it gets the BTUs from the airstream typically. You have what is called process water. That's not what we're going to be talking about here. Process water is used to cool a process. Maybe you're cooling a computer, for example. You've got a rack of computers. Like I've got water cooling on my computer right next to me here. That is process cooling. I've got a process load that I'm cooling. That is different than going and running chilled water into a coil and then cooling an airstream. That's what we're going to be focused on here. But as I mentioned, chilled water, it uses this thing called the refrigeration cycle. Now, if you've heard what the refrigeration cycle is, this next minute will probably be pretty basic for you. But I encourage you to listen, because when we're looking at the refrigeration cycle, we're not looking at it through the lens of a mechanic. We're looking at it through the lens of a BAS professional. A mechanic is going to be concerned about pressure. They're going to be concerned about refrigerant temperatures, things like that. As a BAS professional, we are more so concerned about the things affected by the DX process, by the refrigeration cycle process. So we're more concerned about things like entering and leaving water temperature. We're more concerned about things like chiller load. So whereas the refrigeration cycle is important for us to understand so that we understand what part of the chiller we're dealing with, we're not going to be troubleshooting compressors anytime soon or going in making sure that expansion valves are working. That's the realm of the mechanics. So I really encourage you, if you're a BAS professional, understand how the stuff works. But, I've run into a lot of BAS professionals and they're mastering the refrigeration cycle and they're mastering how compressors work and expansion valves and memorizing refrigeration pressure charts. And I'm like, you realize you're never going to use that. I'm not going to say never because that's like my number one rule is to try to not say never. But I can't recall a single time that having that information memorized helped me as a BAS professional. I can't think of a single time having refrigeration pressure charts memorized and state change charts for refrigeration from gas to liquid. It's not important stuff. You've got so much stuff you need to know as a BAS professional. Don't waste your time on that. All right, back to the refrigeration cycle. So essentially, here's what happens, right? And I want you to focus in on these terms because you'll often hear with chillers, you'll hear the condenser side and the evaporator side. I don't know about you, but when I first got into the trade, I did not have a mechanical background. So when I heard the evaporator side of the chiller and the condenser side of the chiller, I just had to play along like I knew what was actually going on, like I knew what that meant, but I didn't have a freaking clue what that meant. And just so you know, the evaporator side is the chilled water side and the condenser side is the cooling tower side. All right, and the easy way to remember that is you've got condenser water. So that comes out the condenser side. But essentially this refrigeration cycle, what happens is refrigerant changes state at different temperatures than water. So when you have a state change, you have a huge transfer of BTUs. And so you're taking advantage of this thing called state change when you change from liquid to gas, gas to liquid. That's a state change. And that allows BTUs to be absorbed and BTUs to be transferred. Well, what happens is you've got this condenser, right? And so this condenser, it basically is exhausting heat. It's transferring heat. In the case of air conditioning, it's transferring heat to the outdoor air. You see these condensing units typically sitting outside of houses. Okay? Then from there, you have this high pressure liquid that goes into an expansion valve because the pressure needs to be relieved so that then the evaporator can then absorb heat, right? And it absorbs heat. And that state change occurs, changing the liquid refrigerant into a gas. Now, this gas refrigerant then goes through a compressor, and this compressor is making the gas high pressure again. So you got the condenser, the expansion valve, the evaporator, the compressor. Now, here's how all this works with chillers, right? So I said you've got the evaporative side, right? So what happens is the chilled water return. So the chilled water supply actually goes out into the building. It's like 42 degrees. And it goes through a coil and it gets a 10 or 12 degree delta. So it goes from 42 to maybe 54 or 52 degrees. And so you're returning 52 or 54 degree chilled water at 100% load. And what happens then is that warm chilled water hits this refrigerant, right? So the water, and this depends on what kind of chiller you're using, but essentially the refrigerant transfers the heat out of the chilled water, goes through its state change, right? Because we're on the evaporator side, so it's absorbing the heat, it's turning into the gas, it goes into the compressor, which then is making it high pressure again, which then now it goes into the condenser. And this condenser is often either on an air-cooled chiller. This is like a set of coils that have fans pulling air through them. Or this is, in the case of a water-cooled chiller, hence the name water-cooled, you are going and using condenser water that then goes to a cooling tower and uses the evaporative effect. So this condenser water is taking the heat out of the refrigerant. So you got this refrigeration cycle going on inside the chiller, and then that then is transferring heat to the condenser water and absorbing heat from the chilled water, okay? So that's how it works with chillers. Now, as I mentioned, you've got these things called cooling towers, right? And cooling towers, their main purpose is simply to remove heat from the condenser water and transfer it to the airstream. Now, you've got a bunch of different terms. You've got load, lift, approach, things like that. I'm not going to get into those at a high level, but basically what happens is you've got this water that is running through the tower, and the tower has a basin with water in it, and you've got water going over the tower. And you want to keep a certain amount of water going over the tower because you don't want to dry your tower and get your tower into all sorts of messy gunk growing inside of it. But you've got these little spray nozzles, right, at the top of the tower. Usually, not all towers are like this, but usually. And then what happens is you've got a tower fan. So first you use the evaporative effect by just letting the air flow through the tower, but then you can actually use the fan as kind of a second stage of cooling to then go and actually pull air aggressively through the tower or push air through the tower. So you can pull it or push. And then that increases the evaporative effect. And then the water goes and cools down because the air outside absorbs the moisture through the evaporative effect. It's just like if you're sweaty and you have wind blow across your arm and it absorbs that sweat, that's evaporative effect. It cools you down. Well, it's the same with that water, and then the water goes back to the chiller cooler. Pretty cut and dry, pretty basic so far, right? I mean, we're just dealing with refrigeration, and we're dealing with kind of two process loops, a primary chilled water loop and a condenser loop. Now, what will often happen is you'll have this concept called primary secondary loops. So you'll have kind of three levels of chillers. You'll have this constant volume air-cooled chiller with a dedicated primary, and that's it. Meaning that piping coming off of that air-cooled chiller is constant volume flow going straight to coils. And that is called a dedicated primary, constant volume primary air-cooled chiller. Then you can have that in centrifugal as well. But then from that point, the sky's the limit. You have this thing called primary secondary loop. So the purpose of the primary loop is to chill water to 42 degrees. With the understanding that using things like variable compressors and chiller staging, you can run chillers very efficiently at partial load and maintain 42 degrees in a loop. And then through a variety of different mechanisms, decouplers, mixing valves, etc., you can go and bleed water into what's called the secondary loop. So the secondary loop is the load loop, right? So your primary loop is the chilling loop, and then your secondary loop is the load loop. That's where all the cooling coils for the air handlers sit, things like that. And what happens is like I mentioned, you have these kind of two processes. You have a mixing valve, which just modulates open to allow water from the primary loop into the secondary loop, to allow it to mix, to cool down the secondary loop. So that's mixing valve control. That's super basic. That is the most basic of basic primary secondary loop control. Now, you also have this thing called the decoupler. And the decoupler is an interesting beast. It's working off this concept called T's law, which is basically that water's going to flow wherever it can flow. And when it does that, it's going to go and have to equal essentially the GPM of the loop. So basically what happens is that water is going to flow the path of least resistance, basically. And without drawing this out for you, this is actually a pretty hard concept to describe on a podcast because it's such a visual concept. But think about it this way, right? So here you are. You're driving down a street in downtown. And you come upon this street and you can go straight, but there's a ton of traffic. Or you can turn right and there's no traffic. Well, with T's law, you would turn right because there's no traffic. So basically what happens is that once a loop, so let's think of the primary secondary example. We've got a primary loop providing 100 GPM. And then we've got a secondary loop that has a pump that's pumping 200 GPM. Well, what's going to happen is instead of that water returning back to the primary loop, it's actually going to be pulled back into the secondary loop. That's the purpose of a decoupler. Essentially, a decoupler is a straight segment of pipe, and it allows water, instead of going through the return back to the primary, it allows it to be pulled back to the secondary. And so what you do in decoupled loop control is basically you'll often have constant volume primary pumps on your chillers. And then once your primary flow is significantly by a certain amount of lower than the flow of the secondary loop, and you've got reverse flow through the decoupler, meaning that the water is being drawled back to the secondary loop instead of going back to the primary loop, then what's going on is the primary system is going to recognize that, and it's going to start to stage up chillers to add enough GPM draw on the primary side to overcome the draw of the secondary side. Did that make sense? I can visualize this because I've programmed these so many times, but I realize for a lot of you out there, this may be kind of confusing. So, I mean, if you think about it, right? If you've got a really, really strong person and he's pumping water, he's got a pump, and you've got a really weak person and he's pumping water, and this water can go one of two ways down the pipe. It's going to go with the really strong person because that person's going to have more water draw. Well, that's what the decoupler is basically. It's the segment of pipe, and then depending on the GPM draw of the two pumps, whichever one is higher is going to draw the water. So if the secondary loop is stronger than the primary loop, it's going to draw more water, which is indicating that, hey, this secondary loop is drawing more water because in most cases, a secondary pump is controlling to differential pressure, and differential pressure is determined by how many valves are open, and valves are open because they need cooling. So if you've got a lot of air handler cooling valves open, then that's an indication that you have a high cooling demand on these air handlers. And because of that, your primary or your secondary pumps are going to stage up even higher to try to meet that differential pressure, that pressure drop basically, as pressure is being introduced by these coils. So that pressure drop is causing your secondary pumps to increase, which then is overpowering the primary pumps, which is saying, hey, we're not getting enough water. You need to turn on another chiller in order to provide us enough chilled water so that we could start closing down these coils. We can start closing down these valves. So that's how this whole decoupled loop works. Now, we talked about staging, right? So I talked about the fourth version of staging. There's actually 4 ways to stage chillers. And this is really important because of all the things you're going to do in building automation, there's a couple things that are really going to throw you kind of for a loop when it comes to programming and installing. So VAVs are pretty cut and dry and pretty simple. Rooftops are pretty cut and dry and pretty simple. Air handlers, when you start to get into mixed air units that have what I call the trifecta damper setup, where you've got an outdoor air damper, you've got a return damper, and an exhaust air damper, that is a little difficult if it is an exhaust air damper that can act independent of the outdoor air and return air dampers. So that's a scenario that can be very difficult to program. Another scenario that's difficult to program is the aspect of central plant control with decouplers or with multiple chillers that are staged. Because here's the thing, when you're doing this, staging chillers by themselves, it's not really that difficult. I mean, there's 4 different ways to stage chillers, and that'll be staging based on essentially load, but not FLA, not full load amps, which is current draw, but rather load being flow times delta T, which is your basic load calculation. Then there's, as I mentioned, load with FLA. There's the PID of the chilled water supply temp set point. So there's that PID output. You can use that as well. And then, as I mentioned, there's decoupler and decoupler position and the GPM of the primary secondary. So those in themselves are not that difficult to code. Once you learn the design pattern to code those different scenarios, it's really easy. The problem stems with a lot of folks get so focused on that they're programming a chiller and they don't think about the system effect, right? And you hear me harp about this all the time. You're probably like, oh God, here he goes again, talking about system effect and systems thinking. But I mean, it's such a lost art in our trade. And it's understanding that, for example, I had this church that I did, and it was a primary secondary decoupled loop, 2 centrifugals, and then a pony screw chiller, and that then fed to 32 air handlers, if I remember correctly. But it was about a half a mile run across this parking lot in order to get to these air handlers. And so there was lag there. And when I say lag, I'm not talking about for you gamers out there. I'm not talking, well, I guess essentially it is the same thing, right? Lag is a delay in the reception of a signal and then your ability to respond to that signal. So basically, we were measuring differential pressure to control these secondary pumps that were in this central utility plant about half a mile away. And the problem with that was, maybe it wasn't half a mile, maybe it was like a quarter mile. I don't know. It was far. It just seemed very far because it was hot in Texas and you had to walk across this parking lot. But the thing is that it was a far distance, a big enough distance that there is actually a delay in the ability to sense the differential pressure in the primary building and then adjust these secondary pumps in the actual central utility plant. And if you hadn't understood the effect of delay and of the effect of the greater system, then you wouldn't have been able to program that. And so that is where systems thinking really came in to benefit, because rather than looking at just differential pressure, we were able to look at average valve position and use that as well as kind of a determination to help us go and control these secondary chilled water pumps. But it was only because we understood that there was an effect on valve position by the chilled water being at a high enough GPM for these valves to actually be at design flow and be achieving their delta T, because almost no one out there does a entering and leaving temperature on the coils. It's just, for a lot of folks, it's not cost effective. And then adding a flow to the coils. I mean, I saw this really cool thing by Belimo. It was a flow sensor, an entering and leaving chilled water temperature, and then it would communicate it back to the cloud. I don't know what the price is. If they got that to a good price point, then that's pretty awesome, because it gives you true BTO load at each individual coil, and now you can totalize that up to control your central plant. But anyways, I'm super far down this rabbit hole. Back to the 4 different loads, or ways of staging load. So the first way of staging load, as I mentioned, is this basic calculation of flow times delta T, right? And what you're doing here is you're looking at your GPM, and then you're looking at the difference between your supply and return temperature. That's delta T. You're timesing that delta T times the GPM of that loop, and that gives you a BTU calculation that you can divide by 12,000 and get your tonnage. And then if you know the tonnage of the chillers, then you're able to understand the load, and you're able to understand if you need to bring on more or less chillers, okay? That only works in certain situations. When you have a pump that is dedicated to a chiller, meaning it's sized for a single chiller, that's not as effective as if you've got, for example, parallel pumps that are sized for the entire primary loop, and they act independent of the chillers themselves. So there's so many different variables there. But that's one way of staging up chillers. When that tonnage that you calculate gets higher than the tonnage capacity of the chiller that's running. And that's like a really cool scenario because you could do really cool things, right? You can have, for example, a 400-ton chiller, and then you can have a 200-ton pony chiller and another 400-ton chiller. And what you can do is, like, if it's 500, you could bring on that 400-ton and a 200-ton. So that way, you're running that 200-ton, maybe you're running that at full load, but now you're running that 400-ton, you're running it at 300, which is kind of a sweet spot, right? That 66%. That's kind of a sweet spot with chillers, where you're able to run them at kind of this optimal load. I think they say that chillers, centrifugals, I think it's anywhere from 1/3 to 2/3 is kind of their optimal. If someone who's a chiller person, feel free to respond to the comments on this podcast episode. I do not profess to be an expert on chiller loading and efficiency curves for chillers, but if I remember correctly, it's somewhere in that 50, 60, 70% that's optimal loading for a chiller. And that's why one of the staging strategies will be to bring on either a pony chiller or bring on a second identical chiller and then have them track load together to kind of, hey, if we run both of these at 60%, that's more efficient than running one of them at 100% and one of them at like 20 or whatever percent. So that's the first stage, right, is just pure tonnage. The second one is FLA. And so a common sequence you'll see with FLA is that you'll see, hey, when FLA is 90% or greater, 95% or greater, and FLA is full load amps. So essentially it's basically the current that is running through the compressor or the machine, the chiller being the machine. So what you'll do, right, is you'll have this chiller and you'll be measuring this FLA, as I mentioned. You'll be measuring it, as I mentioned, like right around 95%, and you'll watch that for a series of minutes. And then this is very similar to a staging strategy where you have minimum on and minimum off time, and you have minimum state change time as well. So it's got to be above 95% for a certain amount of time. Then you'll bring on a secondary chiller, and you'll often you'll have both chillers track the same percentage command. They'll basically track one another, or they'll track a set point if they're identically sized. And then you'll say, okay, once FLA drops below 40% on that secondary chiller, then I will bring that secondary chiller after, 5 minutes. I'll bring that one and I'll turn it off, and I'll have the primary single chiller take off again. So that's an FLA staging strategy. As I mentioned, the decoupler strategy, right? That's number 4. And number 3, working kind of 1, 2, 4, 3. It's kind of backwards math right there. But the third strategy is the PID of the chilled water supply temp set point. And I really don't recommend using this strategy. This is kind of like the crappy of the crappy strategies. And I've seen this strategy a couple times in sequences, but basically what you do is you have a PID loop, and this PID loop is tracking the chilled water supply temperature. and basically you are commanding a load command on the chiller based on this output of this PID loop. Now, there are so many ways this can go wrong. First off, if you don't have the loop tuned properly, it can go wrong. Second off, if you don't have your staging properly set up, it can go wrong because this loop can get out of whack real fast, and then all of a sudden you've got short cycling chillers and all sorts of issues going on, and that's really bad. I just recommend if you see this, you try to steer folks towards an FLA or a tonnage-based strategy. Those are much more tolerant, especially with interstage changes, meaning going from 1 chiller to 2 chillers to 3 chillers. It's just, in my opinion, a better strategy. So those are kind of the 4 strategies for staging. Now, we've went through a lot here. As I mentioned, we didn't really go into sequences per se, but I wanted to essentially give you my thought process and kind of give you some foundational knowledge of utility plants and just thinking through. Remember our process, right? We go and identify our inputs and outputs and what things are going to be turned on, our Boolean commands. Then we move to our analog commands, our processes. So those are our variable things like pump speeds and valves positions, fan speeds, etc. And then we move to our alarm states. Well, you kind of see what we're focusing in on here with this chilled water sequencing. So that's what I wanted you all to pick up out of this, and hopefully that's what you took out of this. I know my brain's a little shot. I've been going through mental checklists because I'm leaving for the Niagara Summit tomorrow morning, and I don't particularly like to fly, and then I'm getting to fly through apparently really bad thunderstorms. So that's going to be epically awesome. But that's my own problem. That's neither here nor there. It's just going to probably keep me awake tonight. So that's going to be super duper nothing like being tired when you're traveling. Anywho, with that being said, really encourage you to listen through this episode, pick up kind of the systems thinking here. And if you want to have a really structured dive through control sequences, kind of like what we went through here, but much more organized with a lot of visual support, a lot of whiteboard support, and you want to learn from all the way from spaces all the way to central utility plants and systems integration and crack units and everything in between, you want to learn how to interpret these sequences so that way you can apply them to your installation, you can apply them to your programming, you can apply them to your sales efforts, to your engineering designs. Well, then I really encourage you to pick up Control Sequence Fundamentals, which you will find at the bottom of the show notes page. You'll find a link to that. And the show notes page, for those of you who are wondering, is going to be buildingautomationmonthly.com/111. And as I mentioned in the previous episode, for this series and this series only, there is the chance that if you go and you listen to, I think it was episode 110, where I had a challenge where you needed to post your sequence, that if you do that, you could win a copy of my Control Sequence Fundamentals course, which is $1,300. So I believe that it's episode 110 where I talked through that. You might want to go back and listen to that. But encourage you to still take up that offer, because that is going to be ending when this episode goes live on Monday, April 16th. So with that being said, if you're going to be at the Niagara Summit, let me know. I really would like to meet you. If you want to do a deep dive on control sequences, this is the one thing I really know from experience can make you a much better BAS professional and really enhance your career. I encourage you to pick up that course. And also, if you've got any questions related to what we've covered in this series, just go into the comment section. Let me know. I'd love to answer your questions. I look forward to hearing from you. And thank you so very much. Hopefully I get to see you at the summit. If not, I will be talking to you all again next week. Thanks so much for being here. Take care. And I really appreciate you listening. Thanks so much. Have a good one.